Now we are looking at a custom gymnasium environment designed for an automated guided vehicle or AGV navigating a factory floor. Okay, so here you can see our libraries, gymnasium, NumPy, Matplotlib, stable baselines, tree for PPU, and warnings. Okay, we can start. This factory grid M inherits directly from the standard gym M class, which provides a boilerplate we need to interact with reinforcement learning algorithms. Okay, so our state representation consists of normalized coordinates for the agent, the target, and all obstacles. Normalizing these values between 0 and 1 helps the neural network converge faster because it keeps the input features on a consistent scale. For movement, here we have a discrete action space with four options up, down, left, and right. Okay, and the reward structure is straightforward but effective. We give a major positive signal of 100 for reaching the goal, a penalty of 10 for hitting obstacles, and a small cost of 1 for every step taken. We also include potential base shaping, which provides a continuous hint to the agent by rewarding it for reducing its distance to the target. Alright, and here in the constructor we set a default grid size of 10 and limit our episodes to 200 steps to prevent the agent from wandering indefinitely. We define our action space as a discrete 4, for example, here, which explicitly maps our four possible directions. And these static coordinates represent the physical barriers on the floor. Our observation space is a box type. We calculate the size by taking four slots for the agent and target, then adding two slots for every obstacle to account for their x and y positions. Okay, at Manhattan, here to calculate distance, we use the Manhattan metric. This measures the sum of the absolute differences of the coordinates. It represents the minimum number of steps required to reach the goal on a grid where diagonal movement is disallowed. Okay, and look at reset here. Every time a new episode begins, we place the agent at the top left corner, I mean 0, 0, and the target at the bottom right. We also capture the initial distance to start our reward shaping calculations. What is next? Get OBS. This helper function builds the actual vector the agent sees. I mean the normalization logic. We divide every coordinate by n, which is grid size minus 1, to ensure every value falls within that 0 to 1 range. This includes the agent, the target, and the entire list of obstacles flattened into a single array. Continue. Step. This is where the physics of our world happen. When an action is received, we calculate a new pos. Notice we use max and min functions here to act as boundaries, ensuring the AGV stays within the grid limits. Before updating the position, we check if that new pos exists within our obstacle underscore set. If it does, we apply the negative 10 penalty and the agent stays put. Okay, I mean the goal and shaping logic. So if the movement is valid, we update agent pos. If the agent reaches the target, it receives the 100 reward and we set terminated to true. Otherwise, we calculate the shaping reward by comparing the current Manhattan distance to previous one. If that distance decreased, the agent gets a small positive boost. And finally, we check if the agent has exhausted its 200 steps. Okay, let's continue. And to see what's happening during training. We create a simple text-based visualization. We initialize a list of list fields with dots, and we then overlay X for obstacles, G for the goal, and A for our agent. And printing this to the console gives us a quick frame by frame look at the path the agent is taking through the factory. Okay, I'm continue. So we have built our factory world. Now we need to actually run the training process and see how our AGV performs. This function serves as the main entry point for our simulation. First, we create an instance of our factory grid environment and pass it through check environment. This is a vital sanity check that ensures our custom class adheres to the Gymnasium API standards before we try to train on it. Okay, and eval callback definition. To make sure we are actually improving, we set up an eval callback. Instead of just hoping the model gets better, this periodically pauses training 5,000 steps to run 20 episodes in separate evaluation environments. If it finds a version of the model that achieves a high reward, it saves that specific version to the best model directory. And this protects us against the model potentially collapsing or forgetting good behaviors later in the training cycle. Okay, and now we define the brain using the PPO algorithm. Here, the MLP policy. We use a multi-layer perceptron policy because our input is a vector of coordinates rather than raw pixels. And we have tuned several parameters here, the learning rate, of 3e minus 4 uh, here. And this is a standard starting point for PPO. We set n steps to 2048, which means the agents collects about 2000 frames of experience before each update. That's okay. The gamma of 0.99 means the agent values feature rewards quite highly. And we used an and coef here of 0.01 to encourage the agent to keep exploring different paths rather than settling on the first path it finds. And learning part. With everything configured, we kick off the training for 200,000 time steps. This is where the heavy lifting happens as the agent repeated tries to find the goal while avoiding those black obstacle tiles. And once training finishes, we try to load the best model set by our callback. If some reason that file is not available, we just fall back to the state of the model at the very end of the training. Okay, and here some visualization things. We want to see the results, and let me check here. I will summarize here. We reset the environment to get our starting observation. We run a single episode where agent chooses actions based on a string policy. And notice we set the deterministic to true here. This means the agent will always choose the action it thinks is best, rather than sampling from probability distribution. We record the x and y coordinates at every step to plot them later. Plotting parts, and that's okay. And here, main parts. We have our standard Python entry point. This includes a helpful check for missing libraries. If you don't have Gymnasium or Stable Base and 3 installed, this script will catch the error and tell you exactly what command you need to run to get the environment ready. Now, output here. So we have run the training script and we have some very concrete logs to look at to determine how the agent is actually learning. And we will look at first logouts. Okay, rollout, and here eval. Now, in this initial window, look at the total time steps. Here, at this stage, the AP rev mean is quite low at negative 253. This makes sense because the agent is basically wandering randomly and frequently hitting obstacles or timing out before it ever sees the goal. That's okay. And by the time we reach 4096 steps, you can see the EPR means has already started to climb slightly to negative 245. It's still in the negative, but the trend is upward. And to train part here, in the same block, we can see the internal mechanics of PPO update. The loss is at 93.6. This value represents how well the agent's value function is predicting the actual rewards it receives. We also the learning rate held steady at 0.0003 and eval log here at the fifth step mark. Our eval callback triggered a normal test. The valuation reward is negative 200. This tells us that even though the agent is improving compared to its very first steps, it still has not consistently found the goal in a way that overcomes the penalties and collision costs. And notice the episode length is exactly 200. This confirms that the agent is currently hitting the max steps limit and getting truncated rather than reaching the G marker. Okay, here are logs and I will pass. Okay, let's stop here. Final part. Okay, let's look at the actual behavior after 200,000 steps of training. Now, here G and here S. The AGV starts at the green S in the top left. And look at this trajectory. Instead of moving blindly, the agent has learned a very specific safe strategy. It moves straight down the leftmost corridor, keeping a clear distance from that first large black obstacle block. And once it clears the vertical obstacles, it makes a sharp right turn along the bottom edge of the grid. It follows the straight line all the way to the blue G at the bottom right. And the final total reward for this run is here 91.5 because our goal reward was 100. A final score of 91 means the agent reached the target while only losing about 8.5 points to step penalties. And this is a highly efficient path because it avoids all obstacles entirely and reaches the goal in nearly the minimum number of steps required. So we can conclude the training was successful. The agent moved from a state of total confusion, where it just time out, to a state where it has developed a reliable, collision-free navigation policy for this trajectory floor layout.